Chapter 4, we're going to explore systems of linear equations. The backdrop for this project is Pirates of the Caribbean. So if you haven't seen the movie yet, grab some popcorn, watch the movie, and then read this paragraph. We'll be looking at 3 different kinds of systems of equations. For each system, you'll graph the equations on the same graph, and then after you graph, then we'll start looking at the algebra using substitution or elimination. So here's the first one. You have 2 equations. Here's one, here's the other. You could use one of 3 methods to graph. You could solve each of the equations for y, and then graph using the slope and the intercept, the y-intercept. You could leave them as they are and find the 2 intercepts for each equation. So set x equal to 0, find y. Set y equal to 0, find x. You'll have a total of 4 coordinates, giving you 2 different sets of points to connect. Or you could make an xy table. If you choose to make an xy table, then for this equation right here, choose values of x that will simplify that fraction. For example, don't choose -1, 0, and 1, because then you're going to be graphing fractions unnecessarily. Instead, plotting fractions unnecessarily. Instead, choose maybe -2, 0, and 2, or 0, 2, and 4, something like that. Now, I can't graph it for you, but let's say that your lines look like this, or let's say that they look like this. Your job is to find where they intersect, something like this. And it's your job to provide the coordinate in xy form where they intersect each other. You should get a solution in some sort of xy form. There should be a number for x and a number for y. Your solution is a coordinate. For the next part, you already know the answer, because the algebraic solution using either substitution or elimination should be the same as the intersection that you found on your graph on the previous page. But if you use substitution, you need to isolate one of the variables. So some sort of x equals something, or maybe instead you want to find some sort of y equals something. If you chose to graph using y equals mx plus b, then you should already have that nice format. So you're going to solve or isolate one variable and plug it into the other equation, find the other variable, come back and grab the first. But if you use elimination, then you'll find some sort of factor to multiply. So something here that'll give you additive inverse coefficients. For example, if you can find one x to be 5x, then you want the other one to be -5x, and you might need to multiply one or both and use the distributive property. Make sure to line up the matching terms, and then you can use elimination. Without giving away too many of the good details, if you're having trouble with either of these algebraic processes, you might want to take a look back in your book. But you already know the answer, because you graphed so very well on the page before. So, in the next part, when it says, did you find the same solution? Well, your answer should be yes. You should find the same thing when you graph. The intersection of the 2 equations when you graph them should be the same as the solution you find using either substitution or elimination. If not, go back and find where the algebraic error was. Could have been a graphing error. But find it before we find it. Now, the system that you just graphed is called a consistent system because it does intersect and it's also independent, but there are a couple other options. So, for example, the other 2 sets that we're going to work with, you're going to have an inconsistent system, and then the last one's going to be a dependent system. So that's a little more information than I'm supposed to give you, but you'll see what I mean once you start working on it. Often students think that they've done the whole thing wrong because they're finding weird things. Weird things are okay for problems 2 and 3 because they're supposed to be weird and you're supposed to identify how weird they are. For problem 2, you're instructed again to graph first and then use algebra. So again, with your graphing, you can still choose to solve both of them for y and use y equals mx plus b. Another thing is you could use the two intercepts, and you could make an xy chart. This problem that students find with this is, or the difficulty I should say, is that you're going to introduce some fractions, and there's really not a good way around it, but that's okay because you're 1033 and you can handle fractions. There are a couple options. Sometimes we will solve each of them for y, and instead of finding values for y equals mx plus b, we might toss them into a TI-84 and allow the XY chart to show us which X's we should choose, and that'll help us. We can throw in a bunch of X's and it shoots out a bunch of Y's, and we just pick out the best ones. If you want to come build that little skill, then come see me at Hands-On. But any way you slice it, then you're supposed to graph these two equations together on the same plane. Now, it is an inconsistent system, and we have different vocabulary for the different kinds of ways that we talk about an inconsistent system. For a graph, you can see that a system is inconsistent when they are parallel. But the algebra is very interesting here because substitution and elimination are both ideas where we start by making the assumption that the two lines intersect. Now, if they don't intersect, then the original assumption is wrong, and we lead to a contradiction. So some sort of contradiction, pretend you can read that. So for some sort of contradiction, then we're looking at maybe 5 equals 4. If you finish the algebra, you get 5 equals 4. You get 12 equals negative 2. Obviously, 12 does not equal negative 2. So the wonderful algebra that you did led to something that doesn't make sense. A number is equal to something that's not the same number. And that's okay. So you should say the original premise that the two lines intersect had to have been wrong then, therefore they must have been parallel. So what you're going to say for both of these, that if it's a parallel, like that, or if it's something that leads to a contradiction algebraically, and you're going to find both of them, then you should conclude that these are no solution. This system has no solution. You need to connect the ideas that parallel lines make an algebraic contradiction. Where do they intersect? Nowhere. There's no solution for when they intersect. So the first system of equations we looked at was consistent and independent. Consistent meaning that it touches, independent meaning that it's not the same line. So we can conclude that it does touch, but only in one place because it's not the same line. The second system that we looked at was still an independent system. It's not the same line. However, it's not consistent because they didn't touch. So that's a parallel pair of lines. And now we're looking at the third kind that you might see. So it's the third kind that you might see, and it's the second kind of weird, but that would be a system that is dependent. So a system that is dependent means that it's the same line. It's one on top of the other. Again, I'm not supposed to tell you that. You're supposed to find that out, but you have to show algebraically that that's going to be the same thing anyway. So the other two, you had two lines that you were going to graph. If you use any of your graphing methods for this, you're going to find that one line is on top of the other because they're really the same equation, just one of them is in a costume, so to speak. So this third system is consistent because it does touch, but it's dependent because it's the same line and it touches all the time. So when you graph, you're going to use one of your methods, your solve for y and graph y equals mx plus b. You can use your two intercepts. You can make an xy chart. You can use a TI-84 to help you in those processes, but you're going to get one line that's on top of the other. So if you have only one line drawn on this graph, that's okay because they're the same one. So when you start working through the algebra, we're still going to use substitution or elimination, And both of those methods start with the assumption that there is one place where these two equations cross, and we're going to find it. So, since it's the same line, then we're not going to get a contradiction this time, but we're going to find an identity. It's going to be exactly the same. So when you graph, you're going to find the same line, but when you work out the algebra, you're going to get something like 0 equals 0, 10 equals 10, 5 equals 5. In the last set, you could have gotten something like 5 equals negative 5, or 5 equals 4, 5 equals something that's not itself. But when you work out the algebra with substitution elimination for a dependent system, you're going to get something that is very redundant. Well, 0 equals 0. Well, of course 0 equals 0. That was never a question to begin with. We were not contesting whether or not 0 is equal to 0. There's no x left. What do I do with this? So you get the true statement that 0 is equal to 0, but often students don't know what to call that, so that's what we want to fix. So if we want to find where a dependent system touches, well, it touches everywhere. So we say there are infinitely many solutions. We can't really say all real numbers because we're talking about xy pairs, but for every xy pair coordinate that's in one equation, you're going to find the same xy pair or coordinate in the other equation, and you have infinitely many of those. So it's your job to show that one graph on top of the other algebraically comes out to something redundant like 0 equals 0, and you have infinitely many solutions, and connect those ideas. Now that you have 3 graphs and 3 lovely sets of algebra, then come to either Math Connections or Hands-On Math to get your answers verified. See you soon.